This week we're talking about quadratic functions. Quadratic functions are all of the functions that we get by considering transformations of x squared. So x squared we're pretty familiar with at this point. If we take any of the transformation types we've been talking about for the last few weeks, so vertical horizontal shifts, vertical or horizontal stretching or shrinking, reflections about the x or y axis, those are all quadratic functions. If we want to be a little more formal, quadratics are polynomial functions of degree 2. So a polynomial is anything that we can write as sum or difference of a bunch of terms, each of which looks like some power of x. Degree 2 means the highest power that can show up is x squared. So they can have an x squared term, they can have a x to the first term or a linear term, and they can have maybe some constant. We'll look more at what they look like in a second. But again, it's x squared type things. We're going to dig deeper into these. So again, we've been using them for doing transformation stuff. We're going to look more at how they work, what we do with them, how we solve equations, how we solve inequalities, and hopefully, most importantly, get a little bit of a sense for why we care and why these are important. So some terminology stuff. The shape of the graph, and I've probably been using this anyway, but the shape of the graph is called a parabola. So that's the name for the shape of that thing. That's a particular type of a thing that we call a conic section, but that's just the name of the shape. The vertex is this point that we've been using all along to keep track of our transformations. For the transformation stuff, the reason we've been using that is because it's sort of visually distinct, because it's where the graph changes direction or turns around. So sometimes we call that a turning point because it changes direction like that. But what it also represents is the maximum or minimum value of the function. Because we've got this parabolic shape, for this one in particular, the vertex, specifically the y-coordinate of the vertex here, is the lowest that function ever gets. We've done enough stuff with x squared and transformations of it to know that that's relevant for finding the range. If I wanted the range of this one, say this was 1 maybe, the range would be 1 to infinity, right? So that value of the vertex, what that's telling me is that that's the minimum value this function ever gets. A lot of the places that we use math in real world stuff is to optimize things, to find a maximum or a minimum. So this is going to come up in a lot of applications then, because maybe finding that vertex is going to tell us, when I'm spending the least money, or maybe, for a function that's opening downward like this, maybe this is the maximum. What is happening? Okay, sorry, things froze on me for a second there. It's opening downward. This might be a maximum, I don't know, profit or something along those lines. So that's going to come up in a lot of applications anyway. And then the axis of symmetry, that's just this line running through the vertex that acts like the middle of the graph, or acts like a mirror, or again, if I fold over that line, the two sides would line up. So it's a vertical line that passes through the vertex. So if we know where the vertex is, then we know where the axis of symmetry is as well. They stick together. So however the graph is shifted or transformed or moved around, the vertex and the axis of symmetry are, again, sort of stuck together. Okay, so that's some of the terminology stuff. Now there are two common forms that we can write these in. One is called the vertex form, which I'm going to write down, and then I'll tell you why we shouldn't be scared of this. That's how you write it using sort of generic symbols. But A and X and K, or sorry, A and H and K here are just some number, right? Some constant value. So for example, something like 2x minus 3 squared plus 1. Well, we've seen stuff like this before, right? You can probably, and maybe pause the video here and think for a second, but we should be able to look at this and tell how this differs from x squared, from the parent function. This minus 3 shifts to the right. This times 2 is a stretching thing, so it's going to be sort of a tall, skinny parabola. And this plus 1 shifts up. Well, in particular, then, I can read off where the vertex is, because that point that used to be at 0, 0 at the origin on the parent function x squared moved 3 to the right and up 1. So it ends up at the point hk, because h is a horizontal shift, k is a vertical shift, with, again, this one kind of behaving, a little bit backwards because it's grouped on the inside. So really, this is just the familiar transformation stuff, so we don't need to be afraid of the vertex form thing. I'll write that in a friendly pink with several exclamation points and a little happy face, so we know it's all cool. We're just putting a new name on a thing we already know. That's the vertex form. There's also what we call the standard form, which is if we took this thing and multiplied everything out, right? So squared this, collected like terms, distributed the A, and write it as something like this. So again, A, B, and C are just some numbers. This A and this A are the same. That's what we have. That's what we call the standard form. Standard form is nice because it's a little bit easier to write down, a little bit easier to do some things with later on. We'll get into that later. They both kind of have pros and cons, but we'll need to be able to kind of move back and forth between them and get the information that we need in either case. So this is a little bit easier to write down and a little bit easier to work with for some other things, but unfortunately I lose this. Like, I can't just look at this and tell you where the vertex is without doing some other work. The good news is, though, that we have a formula basically for finding the vertex. Unfortunately, we can't really get into why this does what it does without knowing some calculus. But for a thing in standard form, the x-coordinate of the vertex is negative b over 2a. Again, for calculus reasons, so we're just going to have to treat it like a formula. This is one of the very few times that we kind of can't get a good sense for why this does what it does, so we just have to kind of take for granted that it works. But negative b over 2a gives us the x-coordinate. Then to get the y-coordinate, you do what you always do and plug into the function. So this part, hopefully we're not trying to memorize. This just says take the x value you just found and plug it into the function. This part we got to hang on to, though, that the x-coordinate is given by the opposite of b divided by 2 times a. Okay, so in either case then, whatever form we have the thing in, we have a pretty quick way to get the vertex. If it happens to be written out like this, where I can see the transformations, then I can just read the vertex off. If it's in standard form, I can do a quick little calculation here, then plug in. So I have a little bit of work to do, but it's not terrible, and I get the vertex that way, which is good because the vertex is important, because again, it tells us about things like maximum value or minimum value. Okay, one application of quadratic functions is in projectile motion. So lately, my son's current obsession is these like Nerf rockets that he has that like look something like this, and they've got like a rubber band thing here with like a little loop for your finger. So you put your finger through this little loop thing and like pull it down and stretch it out, and then it shoots off and goes pew and goes up in the air and comes back down. So basically, like every afternoon after school, that's what I'm doing, is chasing Nerf rockets around in the driveway. Okay, so this thing with the little fins, and you launch it, and because we live on a planet that has gravity, what happens is that it goes up in the air and then comes back down. I didn't draw that real well, but if we ignore things like, wind and whatever, the path that follows through the air is modeled really well by a parabola. So we can use quadratic functions to describe the way something travels through the air. Um, this changes a little bit if it's, got like if it has an engine, right? Then that's a little bit different. But if we throw something up into the air, kick a ball, or drop something off a building or whatever, um, then we can use a parabola, a quadratic function, to model that. So here's a little more detailed version of this example. We've got this function, and what it tells me about is that y gives the height of the rocket in feet t seconds after it was launched. So I'm using t here rather than x because it stands in for time. This is a pretty common thing to do if we mean time specifically. Zoom out here a little bit. And here's the graph of that function. So again, this is height, and this is time. A couple things to notice. This is quadratic because of the t squared term. It's in standard form because I see the t squared term, a t term, a constant term. They're all separate. Nothing's factored. So it's in standard form. And the fact that this leading term is negative tells me that it's opening down. I mean, also I'm staring at the graph of the thing, so I can tell that way that it's opening down. If I think about the situation, I should know that it's opening down because, I've lived on Earth my whole life. So, I've come to understand that if I throw something up in the air, it's going to go up for a while, and then gravity is eventually going to win and bring it back to the ground. But again, this negative sign out in front of the whole thing tells me that there's a reflection about the x-axis happening. So it's going to be opening downward. Now, one of the things we can find out about this then would be the maximum height that the rocket reaches. We can do that a few different ways. One, I've got it sitting right here on the graph. So I graphed this in Desmos. It'll highlight that point for you. So I just clicked on it and I get the coordinates of the point. Graphing calculators have built-in functions that'll tell you how to do that. I can show you where to find those if you're curious. Or what we're looking for is the vertex. The thing's opening down, so that maximum occurs at the point where it changes direction, which again is the vertex. Since this is in standard form then, to find the vertex, I can use that negative b over 2a thing. So t is negative, or the opposite, of b, 24, over 2 times a, negative 16. Okay, I've got a negative over a negative, so those cancel. 24 over 32. That reduces to 3 over 4, or 0.75. 0.75 is the t value based on how the function is set up. T is time. So I'm just going to write seconds there. That's how long it's in the air before it reaches the maximum height. So 0.75 seconds after I launch the thing, it gets as high as it's ever going to go, and then after that, it's falling back to the ground. If the thing I'm trying to find, though, is the maximum height, I'm not done yet because I just figured out when it happens. What I need is to plug that back in. So find the y value that goes with it. Well, I take my function, I plug in 0.75, which looks like that. All I'm looking for is a numerical answer. I don't really need to work through anything by hand here. I can just type this whole thing into a calculator as it is. And what I get is 12. I cheated a little bit. It's sitting right here. But that again, that's the same thing you would get if you just plug it into a calculator. So the maximum height is 12 feet. Okay. Uh, we'll look at this idea some more in class. We'll talk about some other information we can get and what this looks like in other applications. But this should give us a starting point, just knowing some of the words and how we find some of these things. Um, so we will start there, and thank you for your attention, and I will see you all in class.